Alright, hell yeah. So we have dynamics, and we have work and force and a velocity. You know what I mean? So that's what we're trying to find with this. And we did it 4 ways, and we have really concise solutions, so we can really do this pretty fast. Alright, so when we pull back on this, we have a force diagram. So hell yeah, you have a ton of force when pulling back on the bow. But you can see that you can just draw a line right here and just take the average. So 0 to 312, we get an average force. Now the thing with the work energy equation is it's all about just a force, typically, just like a constant force or an average force over a distance. If you can get those two, like an average force and then the distance, the work is just multiplying those two numbers together. And it's a work in Newton meters or joules, but that determines how much energy you're putting into that mass. Because if you have a mass and you apply a force and it travels, heck yeah, you put some energy into it. And so it increases in speed, and it's the kinetic energy. So the energy that you put into it in joules is the same thing as the kinetic energy increase. It doesn't have any kinetic energy to begin with, and we'll do that equation in a second. But essentially, it's just energy is 1/2 mv squared. This velocity is your final velocity. We can rearrange for velocity, and hell yeah, you just get 2 times that 78 joules, that's Newton meters, divided by the mass, square root it, we get 42.8. So the reason you would do this way is just to, hey, just get some number on it. I didn't even start the video this way because I didn't even know what work was. You know what I mean? Sometimes I totally forget what the hell work is all about. So this was kind of the more complex way. We do have this diagram, so why not just plot it in Excel and get these points and then add a trend line? And then we can actually get an equation for this line. And so that's this equation right here. And so I actually had to look this up because I was just like, well, what is if this is a straight line, the average value is just right in the middle. And I was hella confusing it with finding like the centroid of the area, and it's like, nah, it's just the average value. And I just, for the life of me, didn't understand what that would be. But you still do an integral. You have to take the integral of this and then divide it by this length. And I think that would be like, hey, if you chopped it up into a bunch of pieces, you're finding all these values, and then you're dividing by the number of values that you actually found. So the equation to find the average value, which is higher than halfway, the 156, is going to be, well, this distance, 0 to 0.5. So the general equation is 1 divided by b minus a, the integral from a to b. And so that's what we did. So we have 1 divided by, basically 0.5, and then we do that integral. So x squared becomes x cubed divided by 3. So we just did that, and then we're going to put in our values. So we do the 0.5 first, and then we subtract by putting in 0, but the 0 value is just 0. So hell yeah, so we just spell it out, and we get a value on this, and that is going to be 196.5 newtons. So that is the true average value. It wasn't 156, it was much higher. So that's going to increase our velocity. So again, we use that same equation, and this time I kind of spelled it out. Well, we wanted to find the energy, so we take that average force times that distance of 0.5, and we get 93.5 joules. And in this case, it was just fascinating that just the integral, and I think that is actually, that's like blowing my mind right now. That is a literal proof of hey, if all these are the values of the force, I mean, that is the definition. I don't even have it written. We have it written in the video. The work is the integral of the force vector, with a small change in dx. So I struggle with calculus. It's really hard for me to see like, oh, that means something. I have to take bigger chunks, for it to make sense at all. But yeah, that's really cool that if you just, finding the average value and then multiplying it by the distance is the same thing, the work equation. Now you don't get a vector. After you do this, you're taking the vector of the force, and then, well, it's a dot product. So it's the force in the direction of the direction that you're traveling. You know what I mean? So that's, anyway. And a dot product is a scalar. Okay, so we get that value for that average force that we found with that funky equation times 0.5 meters, we get that as our joules. So we take that energy and say, hey, that change in energy on that arrow gives it a increase in kinetic energy. There's no increase in potential energy. It's not getting higher or lower from the Earth or anything like that. So it's just an increase in kinetic. It had an initial, so that's just a kinetic final minus the kinetic initial, but it had zero velocity to begin with. So literally, the work is just the 1/2 mv squared. And so same thing, you rearrange. You take this 2 to the u, and then you divide by the mass, and then you square root that side, and then you isolate that final velocity. So we got 48.1, which is much higher than 42.8. So hell yeah, that was kind of a fun way to do it. So here is the third way, and this is probably the way they want you. They don't want you to go into Excel for this one, but they want you to chop this up, and they want to say, hey, these are basically straight lines. And so what you can do is take the average value in between these. Now, if it's 0 to 107, that's kind of easy. It's just halfway between 0 and 107. That's 53.7. But what happens if you take the average between 285 and 312? That's where I graduated without remembering or knowing this equation. You just add these two numbers together and then divide by 2. And that's super synonymous with like literally the integration. You're basically slicing this up, adding up all those values, and then dividing by the number of slices. So I still have to re-look at that and be like, well, could I? You know, is it that? It's like integration's wild. You know what I mean? It's a little magic trick, makes your life a little easier though. All right, so now, and this is where you can do extra work that you don't even have to do. But sweet, you found the average force, and that average force is being applied over those little distances. You know what I mean? So again, oh, here I wrote it. So here's the integration. So integration of energy is like, hey, you have a small change in energy is the integral of the force time, like dotted in a small direction. So hey, we're putting 53 newtons in this direction of 0.1 meters. Now this direction is linear, so hey, we get to use it all. You know what I mean? The dot product is like, hell yeah. If it's in line with the direction you're going, you get to multiply these two numbers together. If it's perpendicular, you ain't doing nothing. You know what I mean? So it's 0, and then if you're like doing the shopping cart, putting at an angle, well, you know, maybe you're getting 70%, pushing at a 45, sine cosine. We all know that. That's 0.707. Anyway, so booyah. And so we have this force over this area, and so the integration basically says it's adding them up. You know what I mean? And so we're going to do that. Let's just get to it. So you can take the individual work, the work done over this small little chunk, we'll just call it U1, U2, U3, U4, U5. So the total work from here to here is just the sum of all those. So we're going to take the average. So just as we took the average force here multiplied by the distance, well, and that got us the answer for energy. We're going to take this average force and multiply just by 0.1, add it to this average force times 0.2. That's what we do. So this times 0.1, this times 0.1, this times 0.1. Then we add them all up and we get 97.5. That's compared to 78 for doing just a horrible average. But it's a little bit lower than maybe the exact answer of 93.3. So we get 97.5. This is probably the answer in the back of the book. Even though this isn't what they're asking for. But anyway, energy is equal to that change in kinetic. It's just that velocity. And then you do the same thing. And you get 47.9 meters per second. Alright, hell yeah. And now kind of the fun way that I did the video. Now the video is hella long because, and even this short video is not very good. You know what I mean? We're not making it as tight as possible. But this is where I started. I was just like, I don't want to do work. I want to know, I just want to pretend like I forgot everything about work energy. And I want to use Newton's laws. So Newton's law says force is equal to mass times acceleration. Hey, look, we got a force. And I'm just going to say it's average over the entire course of this bow being let go. Sweet. So we can rearrange this equation for an acceleration. So we take that force of 156, divide it by the mass of 0.085 of that arrow, and we get an acceleration. Hell yeah. 1,835 meters per second every second. Now, is this thing going to be traveling for a full second? No. So what I do is just the guess and check method. Hey, let's just choose 0.1 seconds. Now, the other thing that we need is the equation for acceleration. Write it down. Acceleration is change in velocity, change in time. Now, this is an equation, so you can rearrange it any way you want, and I'm going to solve for change in velocity. Sweet. So that's just going to be this acceleration times my made-up 0.1 seconds, and hell yeah. And this is going to be the change in velocity. And if it's just this number times 0.1, that's 183 meters per second. Sweet. And it started at 0. And got up to 183. Sweet. So literally, the change in velocity is going to be velocity final minus velocity. This is going to be 0. I'm just going to say velocity final is v. You know what I mean? That's kind of what we're trying to find. But now we need to figure out, was that the distance that it traveled? And so we need to say that, hey, if it went from 0 to 183, it had an average velocity of half that. So that would be 91.75 meters per second. And it's that we're going to use for that 0.1. So we're saying this traveled 0.1 seconds at an average speed of 91.75 meters per second. So its distance is these two numbers multiplied, and that's going to be a distance of 9.1 meters. Now, this didn't travel for 9.1 meters, and so we need to guess maybe 0.01. This should say 0.01, my bad. No, it shouldn't say 0.0. No, so what I did here is like, what the hell did we just do to actually get that number? Because it seemed fairly easy. You know what I mean? We took acceleration, took a small little chunk of time that we thought it was. We struck out in the end, but let's go back and see what we did. So we're gonna do 0.01, store that as alpha t. So we took this acceleration and we multiplied it by that change in time. So we got the acceleration and we did alpha a, alpha t, and then we get and with we're gonna do 0.01. With 0.01 seconds, we're going to get 18.35 meters per second for our change in velocity. All right, but let's, I guess what I wanted to do is kind of spell out the equation. So we took that acceleration, and then we took it times a time, you know what I mean? And that gives us our change in velocity. We already started with 0, so that change in velocity is our final velocity. Sweet. But we need to figure out how far we went, because we know this is just a guess. And so we can't use this final velocity because we started at 0 and got up to some speed. So it's linear, but we have to take the average between those two numbers. So that's where we divide by 2. That's the second thing we do. And then once we get the average velocity, hell yeah. And I guess I didn't spell it out. Velocity is change in position, change in time. But for our equation, we need to use the average velocity. I'm going to rearrange this equation to find that distance x. So I say x is equal to, we bring this upstairs, and we get average velocity times that time. And we're multiplying by the time again, you know what I mean? And so to get that x, it's a, acceleration divided by 2 times change in time times change in time. That's 1/2 acceleration change in time squared. As long as your velocity initial is 0, this is your kinematic equation that should ring a bell. But the fact that it's written like this, you know what I mean? It doesn't show the steps. If you write it like this, hey, I'm going to take the acceleration times that change in time. And then I'm going to get that velocity. That's going to be the final velocity. I got to find the average. That's why I divide by 2. That's going to give me the average velocity. Just like you're going an average of 60 miles per hour, how long are you going to do that for? 1 hour. Well, sweet. Looks like you went 60 miles. You know what I mean? So it all just kind of lays out. But now we can do the iterative process once we learn the equation. So we can do this. We can go 0.5 alpha a and then alpha t squared. So we put in 0.01 seconds, and now we get a distance. This we only traveled 0.1 meter. You know what I mean? So that was a bow from here to here, it snaps, and it takes longer than 0.01 seconds. So let's go 0.05, store that as alpha t, and then just iterate. That went 2 meters, so that was too much. Let's go 0.02, store as alpha t, and bring up that equation. This went 0.3, but we need to go 0.5, so we need to go a little bit more. So let's go 0.03, store it as alpha t, and then bring it up again. Hey, 0.8. Oh, we're just kind of, did we do 0.25? Sorry, 0.25. Did we already do that one? Whoop. Okay, so 0.0, oh, we're getting close. So let's do 0.023 stored as alpha t. Whoop, 0.023 stored as alpha t. Bring that equation up. Hey, we're getting really close. So let's go 0.0235 stored as alpha t. And we're getting pretty much right on. 0.0234 stored as alpha t. And 0.0233 stored as alpha t. So hell yeah, I think we're just right on, and we're going to use that one. And so sweet. So now what? Well, we use that change in time to find the velocity. And what the hell equation was that? Well, the initial velocity was just the acceleration times that time. So we're going to go alpha a, alpha t, and we did it. We got 42.8 meters per second. And that's what I did. You know what I mean? That's the fast version. Sorry I can't do it any faster than that. But now for the long version, you know what I mean? And I really like doing videos where I'm just like, hey, let's just do it. And it's unedited. And at one point I tried to do some, I probably go off topic on guessing. And but yeah, we're just not even going to edit that out. So thanks for joining me on this one. And if you want to do the long format, stick with it. All right, thanks for joining me, and that's the video. All right, hell yeah. So we have dynamics, and we have one of the hardest concepts for me to grasp. It's work energy. So that's what we're going to do. This is dynamics with work. So the units on work, if we're using W and we're trying to find the units of work, it's newtons times meters. You know what I mean? So hell yeah. And we know what newtons is. That's going to be the force. So you have kind of a force, and then you have a distance. So you can either do F d, or you can do F times x. You know what I mean? So hell yeah. And how do we use this concept to make a problem simpler? Well, let's read this one. So we have this being pulled. And then as we pull it a distance this way, this is the force that's generated. So when we're pulling right here, ready to release an arrow this direction, we have a force of 312 newtons. Sometimes it's good to use your calculator. 312 divided by 4, about 78 pounds. But it's like 312, what is it, divided by 4.44? We got 70.27 pounds. And now let's try to do the other. If I have 70.27 pounds. No, I'm totally doing this wrong. No. Yeah, there's going to be about 4 newtons in a pound. Yeah, this 4.44. That's a good number to memorize. And then if you don't, you can just do you can take 4.44, do the inverse, and be like, oh yeah, 0.225. That's going to be. So if I have, I guess if I had 70 pounds, I'd have to divide by 0.225. And then we would get newtons. Cool. So now we kind of know that we're pulling back with 70 pounds. See, even just that, making the problem where you're like, you know what I mean? I don't know what 312 newtons is. But when I pull a bow, like what would be like a good force that I could actually pull a bow? Maybe 70 pounds. Sure, I could probably do that. Maybe that'd actually be pretty difficult. It's pretty. That's why archery is kind of a difficult sport. Okay. And so the question is, like, cool, you're going to release it, and you have all this force that's going to be pushing that arrow that direction. And what's the question? Find the speed. Sweet. So now we just want to find the velocity once it leaves. The second the arrow gets to here, this string doesn't do anything anymore. Okay, so this problem, see, and then we're supposed to use kind of work to actually get the answer. But we're not going to do it. We're going to use... And I guess it's just called Newton's laws of motion. Anyway, but we're going to use F equals ma to kind of get a feel for this. Because what's the principles of physics? I think people, when they come back to physics like 20 years later and try to do some problems, if you don't have kind of the fundamentals, and one of the most important classical fundamentals is if I have some sort of mass, whether it's just a little chunk of mass like that, or it's a little square, you know what I mean? If I got some sort of mass and I put a force on that, put a force on that mass, guess what? We're going to have motion. You know what I mean? And it spells it out. You know, if you know the number of force and you know the number on the mass in kilograms, so if we know this force in newtons and we know this mass in kilograms, sometimes I swear it's just like, I don't even do this. You know what I mean? Like what? So like we should. And what's the number that we get for motion? Well, we get a number for acceleration. Now, we should be excited, but I don't know. The definition, acceleration is kind of a funny thing. So that's why any problem, I always write the definition of acceleration, kind of the equational definition. So acceleration is change in velocity, change in time. Cool. And then write both of them. So we write velocity as change in position, change in time. So acceleration is also, you know what I mean, a very small change in velocity with a small change in time, so dv dt. But basically, I think you don't even need to kind of know that one. Just know that, hey, it is the change in velocity. So the number on this, and the units for acceleration, so I guess let's come down over here. Units on acceleration is going to be meters per second squared. Now what I would do, I mean this is also, it's like, I would not write it like this. I would write it like this. Meters per second divided by seconds. And this is acceleration, because this is going to be your change in velocity for every, you know, unit of time. And we just have 1 second. So you can say this acceleration is a change in meters per second divided by 1 second. And now, I don't know, just kind of any way that you can make it simpler. And so cool, once we get that, so and then even just the fact that this equation is written like this, you know, always kind of undo it, you know what I mean? Solve for acceleration. So we can say that acceleration, bring the mass downstairs, so we have force divided by mass, and now we have an equation. Now we can actually find the number on acceleration if we know the newtons and force in newtons, and then the mass, the number on that in kilograms. Hell yeah, we're going to get this acceleration in meters per second per second. All right, hell yeah, that number is what we're going to get with those units. All right, hell yeah. So, but this is where, you know, people aren't going to do this F equals ma, Newton's laws of motion, when we come to a work problem, because you're going to run into this. So this is what we're going to do. So let's do, there's a couple ways we can do this. We can just say, hey, maybe this force is just 312 the entire way. You know what I mean? When we pull back, we got 312. So that's the other thing, is kind of how to read a graph. You know, we could do that. We could just say the force is 312 for the entire, you know, length of this. And that's going to give us a speed of the arrow that's too high. The other thing, we can come in here and just kind of draw a line right here. And we can just say, hey, when we pull back, at the start we're not pulling any force, but then at the end we're pulling 312. Because this is also, you know, something you have to get used to in doing physics problems, is kind of finding like the average. So if I pull 0 to 312 linearly, you know what I mean, it's as if I pulled half 150 plus 6, so 156. It's like I pulled 156 newtons for that entire distance, you know what I mean. So I pull 156 newtons for 0.5 meters. That's the force that's going to act on that arrow until it gets from 0.5 meters to starting to fly away. There is no difference between having a string that puts a constant 156 Newton force on that arrow until it releases, then a force that when you pull is linear from 0 to 312 newtons. When this force gets released, it would apply, both arrows would travel the same speed. And so I don't know where we should start. You know what I mean? Sometimes I like to do that. Just like, hey, if we solve for this, we're gonna guess high, and we're definitely gonna get an answer and a velocity that's way higher. Or, you know what I mean? We might as well solve true to form. Now, if I was just by myself, maybe I would do this, but I'm not going to do that. You know, might as well, if we're going to put minimal effort in, we might as well get an answer that's kind of close. Okay, hell yeah. So we're going to go back to F equals ma. Again, you can say newtons is equal to kilograms, meters per second, You know what I mean? Kind of the units on acceleration. And we can rearrange, and we can say that acceleration is force over mass. And now we're going to say that we're going to have 156 newtons divided by the mass of this arrow, 0.085 kilograms. Hell yeah. Now, if we have all day, you know what I mean, this is where we should just be kind of using our guessing skills. So I'm going to say that, hey, this is the one guessing skill that I like. Hey, we have a 1 right here, and we have an 8 right here. So cool. I can say 1 divided by 8. Like, do I know what that is? Well, I do know what 1 divided by 4 is 0.25. 1 divided by 8 is 0.125. Okay, so there's 2 ways to kind of guess. Like, I don't mind just saying 1 divided by 8 is, and then we're going to have a multiple of 0.125. I don't know. We'll see. We'll see if I actually want to do that. Yeah, I guess let's use the guessing skills. So how would I do this? I would say 1 divided by 8 is 0.12. I wouldn't do that. I would say that this is this is almost 100. You know what I mean? So I would just, in my mind, say this is almost 0.100, and then 1 divided by 1 is 1. I would call it good, and then I would say this is 100 divided by 0.1. And then I would say this is 10 to the 2 divided by 10 to the negative 1. So 10 to the 2 divided by 10 to the negative 1. Oh, yeah, see, even, like, I'm glad I'm doing this, because I bring this upstairs, that's 10 to the 2 times 10 to the 1. Okay, so we're actually going to get 10 to the 3. It's going to be a bigger number. Yeah, no dub. Dividing by a smaller number gives me a bigger number. And, yeah, so now I can just kind of, yeah. It's interesting. Even that guessing skill that I just did was probably horrible. You know what I mean? I should have just easily saw this as 100 divided by a tenth, and that's going to be about 1,000. So right now we got an acceleration of about 1,000. Yep. If we did it this way, this gets us kind of more accurate, but 1 divided, this isn't 1 anyway, it's 15 anyway. So Alright, hell yeah, though, enough said, though, you know what I mean, because if we do this into our calculator, hopefully we get something that's about 1,000. If we got something any different, then we would have to be like, oh yeah, we need to figure it out. So yeah, we have, and definitely it's in the ballpark. So we have an acceleration that's 1,835 meters per second. That's the units on this. Meters per second per second. So in 1 second, this arrow is going to go 1,835 meters per second after t is equal to 1 second. That's what we're saying here. And that's really fast, because you would actually double this and add a little bit more. So maybe 2,000 becomes 4,000. That would be 4,000 miles per hour. So converting meters per second to miles per hour, it's times 2, but it's actually 0.225. And even if we did that, we would have times 2 is 3,200, and then a tenth of this is going to be 180. So we would have 180, 180. That's going to be 360, and cool. So we're already up to 3,560. Oh yeah, I guess it's not too close. So 1835 times 2.25. No, why is my guessing skills just awful? Oh, this should be 30. Double 18 is 3,600, and then a tenth is going to be 180. It's about 200. So we have 200 and 200, and then another 100. So we almost have 500 plus 360. That's going to be 4,100. And it's more than 2.25. I think the conversion may be just a little bit more. But anyway. Alright, so hell yeah. So 4,000 miles per hour. But we know this arrow doesn't travel 4,000 miles per hour. So now what gives? You know what I mean? Because that's the issue when you get acceleration. You're not accelerating for a second. You're accelerating for a shorter period of a second. Because this is the other thing. Let's say we did accelerate from 0 meters per second, which is the arrow. When the arrow is right here, the velocity of the arrow is 0 meters per second. And let's say we do accelerate it over the course, and this is going to be t equals 0. Let's say we do accelerate it over the course of a second, t is equal to 1, and we put this constant force of 156 newtons on it over that entire second. That means what this says is we're going to have a change in velocity of 1,835 meters per second. So we're going to go from 0 to 1,835 meters per second. Cool. And so now the question is, like, how far did we go in that 1 second in this hypothetical? And I think this is crucial for your mind to do this mental math. Just at least do kind of this basic, you know what I mean? And let's go to an example of cliff jumping. You know what I mean? This is you're going to jump into some water, and yeah, you might fall for a couple seconds. You know what I mean? So you want to know, and we know our acceleration is due to gravity. It's going to be 10 meters per second per second. So this is t equals 0. You're going to have a velocity of 0. But at t is equal to 1 second, now the question is, well, we already found our velocity in this problem. This is going to be our velocity at t is equal to 1. And here, yeah, after 1 second of cliff jumping, you're going to be going 10 meters per second. So, and double that, you're going to be going about 22 miles per hour. And if you fall for 2 seconds, you're going to be going 44 miles per hour. Because you're always increasing your speed every second because this acceleration for cliff jumping is constant. Now we come back over here and we see that and if we have a constant acceleration, that means that there is a constant force of gravity that is pushing our body towards the center of the earth. And the reason that's constant is just because that force is, the force of gravity is gravitational constant, mass of you, mass of the earth, and then the radius between the center of the earth and to where the center of your body is, which is essentially just the radius of the earth. But this number is so large that you just being on a tiny cliff does not change that number hardly at all. So the force of gravity is just very constant when you're falling near the surface of the earth, like cliff jumping. Alright, hell yeah. So yeah, I think we all understand that acceleration of gravity is constant. But a lot of our problems is, but there's two things going on here. Acceleration of gravity is constant is because this force is constant. You know what I mean? Because if we go back to F equals ma, we have the acceleration of gravity is constant, the force of gravity is constant, cool. But if in our problem, this force of pulling this bow back is not constant, you know what I mean? So that means our acceleration is not constant. These aren't constant. But we're just saying, hey, we can figure out that this force could be constant. These two things are the same. Having a linear force up to 312 and just an average force to 156 over the course of this distance. Those two things are going to generate the same speed of that arrow. So that's real, that would be an important concept. That's the only way, that's the one way that I can make these problems simpler. I can see that. And now we're just going to use this 156 newtons. It's going to generate an acceleration that's constant over whatever time period. But the time period, this is t is equal to 0 seconds. But hey, when this arrow gets to here and releases, it might be 1,000th of a second. Probably not, maybe 100th of a second. Maybe between 100th and 1,000th of a second. I have no idea. That's what we're going to find out. Okay, so let's go back to jumping off a cliff. Now the question is maybe how far are you going to travel in 1 second? So we're going to say, hey, what's your distance x at t is equal to 1 second? Well, we want to know that. And so we say that we have 0 velocity here. We have 10 meters per second here. You need to find, the take-home point is you need to find the average velocity. It's 5 meters per second. And when we find the average, it's no different than being like, whoa, like, hey, this force was 0 and then it's way up here. Can't we just find the average? Same thing here. We have a velocity of 0 here, a velocity of 10 meters per second. Well, isn't it just like we traveled 5 meters per second over that distance? And yes, the answer is yes. You can say that it's not like we traveled 0 meters per second over the second. We definitely didn't do that. And we also didn't just start out going 10 meters per second and continue to 10 meters per second, because physically we fundamentally started with 0 velocity and we got up to 10 meters per second. So at no point were we ever going 10 meters per second except right at this very last little bit when we reached a second. So hell yeah. But this still is kind of counterintuitive. I bring up this graph of what's the simplest thing I can think of? Let's say we're in a car and we're going to drive from 0 miles per hour, and then we're going to slowly increase our speed to 60 miles per hour, and we're going to do this over the course of 1 hour, and then the question is, how far did we go? So we're going to say, well, it's maybe easy to see that we had an average velocity of 30 miles per hour over the course of that hour, and so our distance traveled is 30 miles. This is the one. I don't know, if I come up with a better one, I'll use it. But this brings up a fundamental of why after 20 years are you going to forget how to do physics? I think it's because the true understanding of some of these equations, you need to kind of go back to a proof of why they work. And what I like to do is, alright, sorry about that, camera cut out. But yeah, what I like to do is take a proof, and then what's the simplest example of a proof that I can't forget. Even over the course of 20 years, I totally understand. Well, yeah, I might even forget this concept of hey, how far do I go when I jump off a cliff? My velocity goes from 0 to 10, but then what? Because I swear, even after coming back to this stuff, I totally forgot the average equation. If I'm going, so if when I jump off, t is equal to 0, my velocity is 0, and then after 1 second, my velocity is 10 meters per second. What's my average velocity? That might be easier to see. It's just going to be 5 meters per second. But now, let's go to t is equal to 2 seconds. My velocity is 20 meters per second. What's my average velocity? And, even this might be maybe easier to see, but maybe you kind of want to know the formula for it when you have something, when it's just not nice numbers. But the actual formula for this is you add the velocities together. So my average velocity between 1 and 2 seconds is going to be the velocity at 1 plus the velocity at 2 divided by 2. And so we're going to have 10 meters per second plus 20. That's going to be 30. And so we're going to have 30 meters per second divided by 2 is 15 meters per second. But if it's just weird to like forget how to do stuff like that after taking such a break from, you know, math and physics and stuff. So, but hell yeah. So that's where this little diagram just always reassures me that, hey, if I have one value here and then at another time I have a different value, well, and you know, maybe it is like just like this. This is I increased my velocity all the way at the end. Well, then my average velocity isn't going to be a half, but at least this gives me a starting position, you know, and then it could be like that. So our average velocity is going to be a little bit higher. So just guess. Maybe it's just 165. All right, so hell yeah. But then always going back to this little diagram, so if we go if we have an average speed of 5 meters per second over 1 second, well, we went 5 meters per second. But now if you do at time is equal to 2 seconds, it gets a little more complicated because now we're going 20 meters per second, and our average speed is 15 meters per second. The total distance that we travel in this time period is the average speed of 15 meters per second times 1 second. And so we go 15 meters. Now, does that mean that we're at the 15 meter height? If, you know, no, we actually have to add this. So we go 5 meters here, and then we go an additional 15 meters here. And so now we're at 20 meters. Yeah, so even though this is kind of a simple diagram, it's good to take it to 2 seconds because, you know, that might be where your problem starts. And so if we had a force diagram that looked like this, it didn't start at 0 to go up to 312, but it started at 156. Like just right off the bat, you had to pull 156, and then you go up to 312. Well, then what's the average here? You know what I mean? So let's do that. 156 and then 312. Well, the average here is just halfway between 156 and 312. And so what's the equation for that? Well, it's 156 plus 312 divided by 2. And booyah. So let's do that one. Okay, that would be 234. Cool. But our problem doesn't start here linearly to go to here. It starts at 0, it goes to there. All right, so I'm going to grab a new sheet of paper, but why we did this is because we have a number for acceleration that's really large, and it's it is the acceleration. It's not nonsensical. It's just interesting because we don't have a second of acceleration. This arrow isn't traveling for a second. When cliff jumping, you might be traveling for a second and your speed's increasing by 10 meters per second just because, hell yeah, most cliffs that you jump off of will be 2 seconds of free fall and probably not too much more. That's a 20 meter cliff, and so that's going to be kind of at the upper limits for recreational jumping. Okay, so hell yeah. But if you just jump off a flight of 3 stairs, you know what I mean? Just jump off from 3 stairs to the bottom. Maybe you want to know how fast you're going. Well, you're accelerating at 10 meters per second for every second, except that you're just not traveling you're not in the air for a second. This arrow isn't going from here to here in a second. It's much less. So, all right, so that's going to be the next thing that we tackle. All right, hell yeah. So let's write this. Acceleration is 1,835 meters per second per second. This is our acceleration using an average of 156 newtons on an arrow that weighs 0.085 kilograms. And so, what should we do? I think we should just guess. You know what I mean? So let's write our equation for acceleration. Acceleration is change in velocity, change in time. This acceleration is 1,835 meters per second per 1 second. Well, cool. can't we just have the change in time just be like a tenth of a second? So if we do that, I mean, this is the number for our acceleration. So even that's maybe kind of hard. So this number would be right there in this side of the equation. This change in velocity is kind of what we want, and now we're reducing this change in time. So we're going to make this 0.1 seconds. So if we make this 0.1 second, and this acceleration still has to be 1,835, I think that's kind of the tricky thing with this acceleration equation. One thing that I've always said is just, well, hey, it is an equation with three different things. You can rearrange this three different ways. You can solve for change in time. That's going to be change in velocity, bring the acceleration downstairs. Or you can solve for change in velocity. That's going to be acceleration times change in time. And this is kind of what we want. So we have the number on acceleration, and then we have change in time. But even just that, the second you're going to like throw these equations around, did we lose our minds and not understand the principles of what's going on? Do we need to go back to our cliff jumper and be like, I'm not going to jump off a cliff where I have 1 second of free fall. I'm going to jump off some stairs where I think I'm going to have a tenth of a second of free fall. You know, just to fly to 3 stairs. Okay, sweet. So then my acceleration is going to be 10 meters per second, but I would have an increase of speed. I would go from 0 meters per second to 10 meters per second had I been in the air for a second. But I'm going to do a scenario where I clock it, and I'm only in the air for a tenth of a second. So, and this speed up is linear. So, I don't know. I mean, I think this is kind of like this, just using the equation. I think you probably lose your mind. You know what I mean? You probably don't. I mean, the cool thing about math is like, hey, if you do have equations, you know that the relationships are mathematically solid. So then you can kind of just tune your mind out to like why they work. But hell yeah. So yes, for this, we're not falling for a second, only a tenth of a second. Our acceleration is just going to be 1 meter per second. But sometimes making these too simple, is almost, 10 times 0.1 seconds is 1 meters per second. But I think we get it. So, and then the other thing is, just guess, this, for these problems, is just like, how fast do you think an arrow can actually go? Just in miles per hour. I mean, just think about it. Do you think it's going to go... I think I've done a problem where if you have whatever those are called, where you can shoot a marble at like birds and stuff. For the life of me, I don't even know what the hell that's called right now. But I think you can get like 200 miles per hour. You know what I mean? Because and then just think of it. You could throw a baseball 100 miles an hour. So when you have mechanical advantage and leverage, and you're doing whatever that's called, or you're doing an arrow off a bow, yeah, let's just say I'm just going to say 200 miles an hour. So I'm just going to say I can get 100 meters a second, which is a little more than 200 miles an hour. But hell yeah! So if I can get 100 meters. So that's kind of the velocity, the change in velocity that we're kind of shooting for. And in a tenth of a second, well, it looks like if that's the distance that we're traveling in a tenth of a second, we could get 183 meters per second, so a lot higher. So that's where we just kind of guessed that this distance, this time from there to there is a tenth of a second. Cool. And that would be our change in velocity if that's the case. But now, let's say our velocity here is 0 meters per second. We think our velocity here is going to be 183.5 meters per second. Cool. And we think this time is going to be 1/10 of a second, and this time is 0 seconds. So what's our average velocity? The average is going to be half of 183.5. Sometimes it's good to guess. Half of 180 is, oh, see, I'm bad at it. So that's 90. Yeah, half of 180 is 90. So it's going to be 91.5 plus 0.25. 91, so we got 91.75. And then just do it in your calculator. Hell yeah. So it's always just good to improve your simple math skills. So here is our average velocity. I mean, we're just totally guessing, but it's good because we said, hey, a baseball player, 100 miles an hour, this thing's got to be higher than that. We got advantage. It's not going to be 1,000 miles an hour. And then what's our limit? Because if I say 1,000 miles per hour, what do I know that's 1,000 miles per hour? Well, that's the speed of the Earth. That's the speed of the time zones around the equator. So the equatorial speed is 1,000 miles an hour. And because every time zone's got 1,000 miles, and then the circumference of the Earth is 24 of those, 24,000 miles. The other thing that I know is the speed of sound is about 700 miles per hour. And so guns, they actually bang, so they could go 1,000 miles per hour. Do I know if a gun goes 2,000 miles per hour? I have no idea. But I know a gun probably is not going 20,000 miles per hour. So that's kind of just guessing with the factor of 10. If I can get within 10 to the 3 for the speed of a gun, hell yeah. And then 10 to the 2 for the speed of an arrow, you know what I mean? Hell yeah. We're just in like Flynn. All right, where are we? All right, hell yeah. So we have this average velocity of 91.75 meters per second. You know, I mean, we went from 0 to that, but we're only traveling this average velocity. So if I said, hey, I'm gonna travel 100 miles per hour, and we're doing it. We're gonna go for a full hour. Okay, sweet. You went 100 miles. But hell no. No one goes 100 miles an hour for a whole hour. Unless you got the freeway all to yourself. But let's go 100 miles. Let's do it at least for 1/10 of an hour. I don't even know what kind of time frame that would be. It would be, yeah, I don't even know. But anyway, there's 12 on a clock. So if there was 10 on a clock, you would have 1/10 of that. And these are 5, yeah, about 5, 6. Is it 6 minutes? Well, yeah, no duh. Because you have 60 minutes in an hour. 1/10 of that's 6 minutes. So hell yeah, you're going to go 100 miles an hour for 6 minutes, but only for 1/10 of an hour. Hey, you're going to go 10 miles. That's the same thing we got going on here. We're not going 91 meters per second for a full second. We're going 91.75 meters per second for 1/10 of a second. So I don't even need to do an equation on this. I can just see that I'm going to be going I'm just going to round up 9.2 meters. Okay, sweet. But guess what? You know, so that was our initial guess, and it's awful. But we had to start somewhere. And then we totally see that, hey, you can't travel for 9.2 meters with that force of 156 because we only pulled the bow back to 0.5 meters. So we're just using like a guess and check method. You know, this is 10 to the 1. This is, well, it's kind of close to 10 to the 0. You know, be like close to 1. So we're going to say we're a factor of 10 off. So we're going to change our time to 0.01 seconds. So now it was really easy. It was easier to see, hey, if I'm not going to fall off this cliff for a full second, and I'm not going to go 10 meters per second. I'm just going to jump off some stairs at 1/10 of a second. But let's say I find something to jump off and it's 100th of a second. What's my speed? I wrote the wrong thing down here. I apologize. Yeah, that's a real bummer. But it just shows, yeah, it's interesting where you make mistakes. So the acceleration is 10 meters per second for a full second. I'm only jumping off a flight of stairs 1/10 of a second. That means my velocity is going to change by 1 meter per second. So in that case. All right, do I need to slow down? Or can we just do this? So we're going to be accelerating at 1,835 meters per second, not for a full second, not for a tenth of a second, but for a hundredth of a second. So our change in velocity is going to be a change of 18.35 meters per second. That's going to be our change over that 100th of a second. Cool. Our average velocity is going to be not 91.75, but 9.175. And then we did that for a 100th of a second. So we got 9.175. This is our average speed. If we went for a second like this, we would go 10 meters per second. If we went for a tenth of a second, we would go 0.9 meters per second. But we're going for a 100th of a second. So we're going to go 0.09 meters per second. And you can see that now we totally... see, I'm just saying things that are... I always like, you know, when I'm saying distance, why did I put meters per second? I don't know why I do that. But here's our average speed for a 100th of a second. And when we go this speed, let's talk it out again. If we're going 9 meters per second for a second, cool, we went 9 meters. We didn't do that. Did we go 9 meters per second for a tenth of a second? If we did that, we would go 0.9 meters. We didn't do that either. We went for a 100th of a second. So that means we went 0.09 meters. And then we just found out that so we overshot it here, we undershot it here. Because we actually this bow has that force for 0.5 meters. Alright, sweet. So now, let's just do the prices right and find a change in time halfway between. So we're going to go 0.05 seconds. What's our acceleration? And let's go back up here. So let's say we'll do one easy, one hard. We're going to free fall for a half a second. Alright, now we can just whoop these out. Our velocity is going to be 5 meters per second. Hopefully that was whooping it out. But let's say we only travel for not a half a second, but 0.05 seconds. Cool. So our speed must be 0.5 meters per second. That's going to be our change in velocity over 5/100ths of a second. And how did we? So then, this is, if you, especially you can find something that's intuitive. You know what I mean? Like 0 miles per hour, 60 miles per hour over the course of an hour. I can just easily see that's 30 miles per hour. What equation did I use to get this 30? I added 0 plus 60 divided by 2. You know what I mean? So that's that average equation that we use. So we can do that same principle when if I free fall for half a second, I'm going to go 5 miles per hour. So what did I do to get that? Well, I took that acceleration of 10 meters per second squared, or 10 meters per second, and then multiplied by the time of 0.5, a half a second. And when I multiply those two together, seconds cancels, and I get 5 meters per second as my change in velocity. Okay, so I want to multiply this by 0.05 seconds, and then everything works out, and then I have a change in velocity of 0.5 meters per second. So hell yeah, so we just did that. So at the end of the day, I'm just taking this acceleration, multiplying it by the change in time. So this is how I would want other people to learn, or I don't know, I think it's, what I'm trying to do is pretend that I could have learned this way in college. You know what I mean? After going to college and then 20 years later being like, yeah, this is the way I should have been teaching myself. It's the way that I really learn. And so now we're going to go back to this equation. Does this equation make sense? Change in velocity, that's what we want to find, is going to be that acceleration. It's going to be that 10 meters per second jumping off a cliff times 0.05 seconds. Hey, that's going to be 1, 2, so we go 1, 2, and we're going to go 0.5 meters per second. That's going to be our change in velocity. Hell yeah. So now let's use this equation on this one. So we're going to say our change in velocity is this acceleration of 1,835 meters per second times, and we think this one's going to be fairly accurate, 0.05 seconds. But I bet you it's not. I bet you we need to do like a quarter or a third, but we'll see. Okay, hell yeah. We multiply these two together. Let's use our guessing skills. This is about 0.1 or 10 to the negative 1, but we have a multiplication factor of, if we did that, we would have to divide by 2. You know what I mean? So keep that in mind. Or the other way to do it is maybe this is 10 to the negative 2, and we could always multiply by 5 later. Holy hell. Let's go back to, that's why I really want to just do my own thing. You know what I mean? I don't think, as long as I'm doing my own thing, I'm having a good time, and I think those are teachable moments. So why did this one suck? And how could I get better at this? I was doing 156 newtons divided by 0.085 kilograms. Now, I guess, I don't know. I mean, I guess I have two things going on here that I've never done. This is a multiplication factor of 1.5, so I could just say 1.5. This is a multiplication factor of 8, but it's downstairs, so how do we deal with that? You know? And even though it's downstairs, it is upstairs. That was the revelation. It's like it's not downstairs. It is upstairs. It's multiplying by 8. You do this because scientific notation says this is 1.56 times 10 to the 2. Well, guess what? This is 1, 2. This is, and then this is the same thing as multiplying by 8.5 times 10 to the negative 2. That's wild. You know, that is actually wild to me that we have 8 and then multiplied by 1.5. So, yeah, that's really interesting. And, anyway. Oh, but here's the other good guessing skill. And it doesn't really work if these numbers are really far apart, but it gets you close enough. You can always, if I increase this one by a half up to 2, and then decrease this one a half to 8, then I actually get a very close representation of this guess. Now, if I go the other way and increase this to 9 and decrease this to 1, hey, maybe that's in the ballpark, like 1.56 times 8.5. I mean, you can't say that's 9 times 1. That would just be times 9. You know what I mean? Where 1.5 times 8, that's going to be like that's going to be, well, 2 times 8 is going to be like 16. So it's going to be between 8 and 16. So maybe it's like 12. So 9 was a horrible guess. But let's do this. 2 times 8, you know, that's going to be an overshot, 16. And then the other thing that I've recognized, I mean, I don't know why I'm wasting my time on just guessing, but it is fascinating because you could, it's like mentally, if you want, like, because I can't do this mentally, 1.56 times 8.5, but I can see that they're far away. If it's 7.5 times 8.5, hell yeah, you know what I mean? Just take them inward, so this is going to be 8 times 8. If you take them outward to 7 times 9, it's not as good because we can see this. We can see that 8 times 8 is 64, 7 times 9 is 63, 7.5 times 8.5 is going to be 63.75. So it's closer to, you know, bringing these in towards each other than away from each other. But if they're hella far away, you can always average. Now, if I average between 64 and 63, 63.5, well, 64 might have been just as close as 63.5. But if you average these, you're always gold. You know what I mean? There's no reason you couldn't just take the average. So that's what we can do here. 1 times 9 is 9. 2 times 8 is 16. And what's halfway between? And maybe we want to use our method. 9 plus 16 is 25. Half of 25, I don't know it, but that's going to be 10 plus 2.5, so it's 12.5. So hell yeah. So that's going to be my final answer for this. It's going to be 12, it's going to be, it's going to be 12.5. So this would be a multiplication factor of 12.5 once I'm done. Or I can say it's just 1.25, but then make sure I got a 10 to the 1. So we're going to have, so that's my multiplication factor. 1.25 plus a 10 to the 1. And we can see this is 10 to the... So then I take these down to their base levels. This becomes 100. This becomes 0.01. You know what I mean? I don't go higher. I don't go... You know what I mean? If it's got 2 digits, that's where I put those 2 digits. This has 3 digits. That's where I put those 3 digits. This is 10 to the 2. 10 to the negative 2. I can see those cancel. See, I make this mistake all the time. Holy hell. 10 to the 2 divided by 10 to the negative 2. Dividing by this negative is multiplying by it. So 10 to the 2 times 10 to the 2 is going to be 10 to the 4. Oh, shoot. So I am messing up. This plus 10 to the 1 is downstairs anyway, so it's got to be a negative 1. So that's not a very good guessing skill. But so anyway, so it's not going to be 10 to the 4. It's going to be 10 to the 3. It's going to be 1.25 times 10 to the 3. So it's going to be 1,250. That would be my answer for that. And is it even, like, why the hell is it so far off? Like, why wasn't that a good guess? I don't even know. 1.56 times 8.5. That's going to be 13.26. Am I fundamentally messing this up by, I mean, is this not a true statement? 156 divided by 0.085. Yeah, well, holy Toledo. So fundamentally, that wasn't right at all. This is still 1 divided by 8.5. Damn. 1.56 times 10 to the 2. I thought I was just kind of inventing new math, but no. Just really messing up. So 1 divided by 8.5 times 10 to the negative 2. Oh, that didn't work either. Alright, hell yeah. No, yeah, this, I mean, it has to be divided by everything, so this has to be a positive 2. If I take the inverse of 8.5, if I do that, if I go 1 divided by 8.5 and get that as a decimal, then I'm okay. But other than that, I can't do anything with this. So we just spent a lot of time doing nonsense. I totally apologize about that. Alright, hell yeah. So we got off on a tangent, and I think I had to clip some of the video, you know, because we were just getting into our guessing skills. It's kind of fun to do, but we're kind of at the point where we've kind of developed an equation. So we're going to have a change in time of 0.05 seconds. We're going to assess that. We have F equals ma. We have the force, and then we have the mass of this is 0.085 kilograms, and so we're going to have an acceleration. An acceleration is going to be force divided by mass, 156 newtons, 0.085 kilograms, and that acceleration, 156 divided by 0.085, is 1,835 meters per second, and hell yeah. And then we figured out that, the equation for acceleration, change in velocity, change in time. So if I want to find that change in velocity, I'm going to say that's acceleration times that change in time. So we're going to have 1,835 meters per second times 0.05 seconds. Seconds cancel. And now we're doing things. You know what I mean? So we're, and I guess I just got into like guessing, you know what I mean? I rounded this up, and then if we did rounded this up to 0.1, this is going to be 183, but we have to half that, so it's going to be about 90. Yeah, so it's going to be 900. No, it's going to be 90. holy Toledo, we're gonna have a 90 meters per second be our change. So 1,835 times 0.05, hell yeah, that's gonna be 91.75 meters per second. That's gonna be my change in velocity for that 0.05 second interval of change in time. So now we need to find distance, and I guess we could find distance by saying that velocity is change in position, change in time. And we do have a velocity now. That's the average velocity. Oh, hell no. You know what I mean? We already messed it up, so we should just go back to our, cliff jumper times 0, velocity is 0, time 1, velocity is 10. That means we have an average velocity of 5 meters per second. This is the only thing that we can multiply by this 1 second to give us our distance. So this equation says that yes, in 0.05 seconds we're going to go from a velocity of 0 to a velocity of 91.75 meters per second. So what's our average velocity? Well, it's half this, and it's going to be about 45, 46. So sweet, so we got 45.875. And hell yeah, so now we can use that. So we can rearrange this equation. Hey, what's our change in position? Is going to be velocity times change in time. Sweet. But this has to be average velocity. And we're going to find it's 45.875 meters per second times that 0.05 seconds. And that makes sense, because just like up here, we have that 5 meters per second. We fell for a second. We must have gone a distance of 5 meters. Here we have a velocity of 45 meters per second. We're going to do it, let's say we just do it for a tenth of a second. Well, we went 4.5 meters. But we're not doing it for a tenth of a second. Let's do it for a hundredth of a second. Well, we're going to go 0.45 meters. But we're going to go 5 times this. So, you know what I mean? Or we're going to go half this. So, yeah, we're still going to be wrong. This says we go 2.5. So let's throw it into our calculator. 45.875 times 0.05, and yes, we're still going a distance 2.3 meters. That's way too far. So our change in time needs to be a little bit less. So let's do change in time of 0.2 seconds. And now let's focus on, I mean, it's cool to do this process, but let's see if we can just do it with our calculator now. I think that is such a teachable moment of like, hey, do this, mentally do it, figure out understand what you're multiplying. Don't just rely on an equation, but then once you kind of understand, then you can put the equation to it. So now let's use our calculator to do this. I'm going to do 156 divided by 0.805. I'm going to store this as alpha A. So here's our acceleration. In my calculator is alpha A. I'm going to do 0.2 stored as alpha t. That's going to be that time frame. And so alpha A times alpha t, this is going to be my change in velocity. Oh, hell no. This has got to be 0.02. My bad. So 0.01 was too... Yeah. So this has got to be, we're going to do 0.02. 0.02 stored as alpha t. So alpha A, alpha t. This is going to be my change in velocity, but we need average velocity divided by 2. This is going to be my change in, this is going to be my average velocity over 0.02 seconds. What's my distance? Times alpha t. Sweet, so we just went 0.36 meters. But we know that when we pulled this bow, we went 0.5. Okay, hell yeah. So let's kind of just prices right it out and increase this. But now, see how fast we can do this? We're still just kind of guessing and checking, but we're using the actual numbers that make sense. So 0.03 stored as alpha t, alpha A, alpha t. This is the change in velocity divided by 2 is the average velocity times alpha t. This is so that was too much. So 0.03 was too much. So how about 0.025? 0.025 stored as alpha t. So now we're 25 thousandths of a second, or about average of or 3/100ths of a second. In between 2 to 3/100ths of a second. That's how I'm going to say that number in seconds. So acceleration times time. This is my change in velocity. We need the average velocity divided by 2 because we start with 0. You know what I mean? If we didn't start with 0, then we'll add those two numbers, divide by 2. But here's our average velocity times, and then so it's meters per second times time gives us meters. So times alpha t, and we get 0.57. Hey, we're getting pretty close. So I'm going to go 0.024. 0.024 stored as alpha t, alpha a, alpha t divided by 2 times alpha t. And now, even just right now, let's really dial it in. What are we saying? We're saying that we're taking acceleration times change in time. This is going to give us the max velocity, the velocity that we do. So this is going to be the change in, we want the average, but we started at 0. So we're going to take this, divide by 2. Once we get this is our average velocity, but we need to multiply by change in time. And then you can totally see this is the kinematic equation. This is 1/2 acceleration change in time squared. You know what I mean? And there's no additional thing right here because my initial velocity was 0. So hell yeah. So that's literally all we're doing. But to use this equation is to not understand the fundamentals of what's going on. You know what I mean? The second you just gravitate towards an equation without going back, and that's why jumping off a cliff, going 1 second, going 2 seconds can totally spell it out. Because let's say you wanted to take, let's do this. We're going to set this, this as my stopwatch. This is my 0 point. Oh, man. Yes, I want to do this, but it's just mentally just a little bit harder. So right here, I'm going to say this is time 0. Someone's going to stopwatch this person. The person already jumped a full second, but they're going 10 meters per second. And in another second, they're going to be going 20 meters per second. And we want to know what distance from this point do they travel. And so we're going to say, what do we need? Well, we need to know, the time frame. So we actually clocked them at 1 second, and then they splashed in the water. So cool. Sometimes that doesn't really work out, but hell yeah, 1 second. So now what do we know? We know that the acceleration, and let's say we don't know this is 20 meters per second yet. Acceleration of gravity is 10 meters per second per second. So in that 1 second, they're going to be going 20 meters per second. We're going to find the average velocity. That's 10 plus 20 divided by 2. That is going to give us 15 meters per second. That's going to be the average velocity. Now what do? We multiply by that change in time of 1 second. And that's going to give me a distance of 15 meters. So let's run through that. How did we find this distance? We said what did we do first? We said we took this initial velocity. I don't even know what we did. Oh yeah, hell yeah. Well, let's just start with this change in time. We have a change in time of 1 second. We definitely clock that. We know our acceleration is 10 meters per second because that's gravity. And this says we're going to get a change in velocity of 10 meters per second. But we're already starting at 10 meters per second. So keep that in mind. So velocity V naught is 10 meters per second. So, but we need to know this final velocity. That's going to be that initial plus our change in velocity, so 10 plus 10, that's going to equal that 20. Once we find that 20, that's going to be the velocity final. But that's where I think the kinematic equation when you're doing velocity initial, velocity final, is too much, you know what I mean? It's just, it makes your mind melt. But hell yeah, so once we do get this 20, we're not done yet. We still have to take that initial velocity, and then we're going to find the average velocity by taking velocity initial plus velocity final divided by 2. Once we get that average velocity, then we can find the position change, I guess change in x, by taking that average velocity change in time. So let's go back and see what we did. So this is going to be v naught plus velocity final divided by 2 times change in time. But to get this velocity, no, that is velocity average. Yeah, so velocity average times change in time, that's going to be change in position. Which one of these did we not know? We didn't know the velocity final. Cool, so let's, and we can just say this is just 1/2 velocity initial plus 1/2 velocity final. Cool. And what was velocity final? Velocity final was going to be velocity initial plus, well, then that acceleration times the change in time. Whoa, that was velocity final, so that's wild. Alright, hell yeah. And I think we can just do this. 1/2 velocity initial plus velocity final. And we can say this is 1/2 velocity initial plus velocity initial. There we go. Yeah. Holy Toledo. That's where they add up. Because we're going to have 2 of them. That's going to cancel that half. But now we're going to have plus acceleration change in time. So now we're going to have, I guess we should totally spell this out. 1/2, 2 times velocity initial plus acceleration change in time. And so change in position is going to be velocity initial plus 1/2 acceleration change in time. Whew, hell yeah. So we did it. And that was brutal. But this shows you that you can get the kinematic the best way to get the kinematic equations is to do the simplest thing possible and then mentally figure out what you're doing and then go back to see what you did to the numbers. And this is what we did to the numbers. We took a couple different things and then we took acceleration and times. That's why this doesn't spell out exactly what we did, because we took acceleration in one of these change in times, then we divided by 2, and then we multiplied by another change in time. Alright, hell yeah. So now that we know that we're dealing with this equation, and we don't have any initial velocity, so hell yeah. But if we did have initial velocity, you would have to add that. And we didn't even do it right. Because this has to be v naught change in t anyway. How did we mess that up? Oh, nice. Yeah. That's why these kinematics is a lot going on. We took a side branch and said, hey, this is the average velocity, but average velocity is a function of f. So sorry, this was just average velocity. Was v naught plus 1/2 a change in t. But then when we throw it into this equation, we multiply by the change in time, and then we're going to have v naught change in t plus 1/2 acceleration change in t squared. Okay, so my bad for totally rushing that. But let's go back to just kind of prices writing this out. We have alpha t is 0.024, so we're going to do 0.5 a alpha t squared. Booyah, we're getting a little bit closer. We're going to go 0.023 stored as alpha t, and then we're just going to pull that up. Okay, so now we're too low. So we're going to go 0.0235 stored as alpha t. Bring that back. Okay, so now we're pretty close. Little tie, so 0.0234 stored as alpha t. Whoops. Alright, so we need to reduce this. Now increase it. Okay, increase it some more. Alright, hell yeah. I'm going to say we're pretty much right on now. You know what I mean? So, booyah. You know what I mean? And we're just kind of playing this game. Alright, hell yeah. One more, I guess. Ah, damn. There we go. Alright, so our change in time for this, and the problem's not even exact anyway. I don't even know why we're working so hard. But we're just saying if this is still, our assumption was this was a linear pole from 0 to 156, we're going to have a change in time of, what was our change in time? Of 0.023, I'll just say 3 seconds. And that is going to cause this, how do we say this? So when we pull it back this distance, we're going to have an acceleration, average acceleration of 156. So the time it takes for this this arrow to get from here to there, that change in time is 0.0233 seconds. Go back to F equals ma. We're going to have an acceleration. We got that number. That's 1,835. We're going to find the change in velocity by taking that acceleration, that number, times change in t, which we just found. That's going to give us the change in velocity. So let's do that. We're going to do 156, or that alpha A. Alpha A is our acceleration, and multiplied by, alpha t is in here. Alpha A, alpha t. And our change in velocity is going to be 42.84 meters per second. So hell yeah. So find the speed at which this arrow leaves the bow that was drawn 0.5. Well, we just did. And in just I wouldn't say a bizarre way. I guess I'll say a bizarre way to do it. But we did it. 42.8 meters per second times 2.25, about 96 miles an hour. Okay, yeah, so I'm kind of surprised that an arrow can travel, almost no faster than a fastball. That's kind of interesting. And I guess, yeah, you can just shoot an arrow and it can leave. I mean, if you hardly pull this thing back, it could have 0 velocity. Or you could have 5 miles per hour up to 100 miles per hour. All right, hell yeah. And this is going to undershoot it because we know that the average force is going to be just a little bit higher than half. You know what I mean? So we didn't know exactly how much. All right, hell yeah. So I love making mistakes because it's the only thing that'll kind of set into my mind, like to not make them again, or like the principles of what's going on. Because there's one thing that we did glaringly wrong. It might have been okay to just say that this was an average force, 156 over the course of the but what we were saying is over that change in time, our average force was going to be 156 newtons. And that's not going to be the case. So we'll have to look at this. This is kind of interesting. Let's grab another sheet of paper. Because these are not time intervals. These are change in position, not change in time. And so, so we need to kind of assess, like, how that, because here was a question. I was just like, well, if I have a force over time and I either do this, so let's say what did we think our change in time was? 0.02. So let's say this is just 0.02 seconds. That's going to be our time frame, and we thought it was 156 newtons. Now let's draw a second graph that says, hey, let's say we start at 156 newtons. There you go. So 156. So force 156 newtons, and then in 0.02 seconds it goes down to 0 newtons. And so actually this is representative of this. You're pulling. You have this string with a force of 156 newtons, and then as you let go, that force tapers to 0. And then we're going to say, I'm sorry, this should be 312, and this should be 312. But we're saying we're having an average force of 156 newtons. So in both these scenarios, our average force is 156 newtons, just like the problem that we were trying to, kind of get a handle on. And so both of these will make the same velocity for the arrow. I don't even know why, but I think that's the case. But if the force is over a distance, and you have this graph, and it looks like this, like if you have 0 force at this 0.5 meters, and then you increase to 312 newtons, this is going to give you a different velocity of that arrow. So now I almost need to turn off the camera and figure out why. Alright, hell yeah, this is really good. Let's go back to our cliff jumper, and we're going to do a really high cliff. And so here's 1 second, that's 5 meters. We said in 2 seconds, we're going to be, so we got 1, 2, we're going to be a total of, let's get this right. So this is 0 and 10. Our next spot is 20, so it's an average velocity of 15. So we're going to be going 15 more. So yeah, we're going to be, if this is 5, 10, 15, we're going to be at 20 meters. So this is at 2 seconds. And this is cool. Because how should we do this? Alright, so in physics, a lot of the times it's good to take a problem to an extreme. And so I think the extreme of this graph is you have a force and then no force. You know what I mean? So there's your 312, and then this is 0. So we're gonna compare it to that having no force off the start, and then the 312. So in this graph, here's your starting point, and you're going this way. Where if you do a time graph, like this would be 0 time, and then your time would be 0.05 seconds. So these graphs are a little bit reversed. So this graph is this graph. Starting at 0, you're going to have 300. But anyway, okay, so let's do that for this. Let's say we can turn on and off gravity. So it's either going to be 10 or it's going to be off. For the first second, we're going to turn it on, and for the second second, we're going to turn it off. And then we're just going to call it. That's going to be our experiment. So if we turn gravity on for the first second, we're going to be going 10 meters per second, and we're going to be going 5 meters. If we turn gravity off for the second second, we're not going to increase. The acceleration is the change in velocity. If that goes to 0, we turn it off, we're not going to have a change in velocity. So then our velocity at the beginning of this first to the end of the second second is going to be 10 meters per second. That's going to be an average velocity of 10, and we're going to travel that for a second, so we're going to travel another 10 meters. We're going to be right there. Okay, hell yeah. So we're going to be at a total of 15 meters. Well, we're going to be going 10. We're going to be going 10 meters per second at 15 meter mark. So now let's turn off gravity for the first second. Yeah, because even just right there, I thought we were, I thought it was like, no, it's going to be the same. But hell no. we're going to turn off gravity for that. We're going to step off and there's no gravity. You're just going to be floating there for the first second. Cool. Then you turn gravity on. So the next second, you're going to be increasing your speed to 10 meters per second, average velocity of 5. You're going to go 5 meters. So this is your position in the second scenario. This is your position in the first scenario. So one scenario, hell yeah, your velocity is the same. That's kind of interesting. Oh man, that's tripping with me. Velocity is the same, but the distance... I don't know if this is actually going to help me. Alright, no, we got to truck through this, because it's going to be representative of this, of like force on, force off. So we're basically taking this graph and turning it into this graph. But the only thing that is a requirement is both arrows have to end at the same point, and what we want to know is the velocity once they do that. So, oh yeah, and it's still not representative. Like, this scenario is still just based on time of that 1 second on, 1 second off. Ooh, this is, man, I almost need to make a scenario where we do this with, distance. Well, let's do that. So we're going to have 20 meters. So we're going to divvy this up 4 times. And for the first half, we're going to turn gravity on. It was either going to be on or off. And then for the second half, it's going to be off or on. And so for the first scenario, we're going to have gravity on. And then we're going to turn it off. And I imagine, I'm just going to guess, I'm going to imagine that this is the better scenario. Like, this is going to have the fastest velocity. Let's check it out. So we're going to have 10, and I think we even need to use our equation. So if we have acceleration is 10, velocity is 10t, and position is 5t squared. Alright, so what we need is the time frame, or what do we need? Yeah, this kind of bizarred me out. Yeah, so we at this position, this is going to be 5 meters, this is going to be 10 meters, 15 meters, and then 20 meters. I need the time, if we're going to turn gravity on, I need the time it takes to go 10 meters. So I'm going to say time is equal to x divided by 5 square root. So I just took the 5 downstairs and then the square root of that to get time. So let's do it. Square root of 10 divided by 5. Sweet. So that's going to be the time. I'm going to store that as alpha t. And now what we need is, what do we need? We need the velocity at this point. Because once we turn gravity off, this is our velocity. And that's it. So, okay, velocity at this point is going to be 10 alpha t. So we're going to be going 14.14 meters per second. And that also means that we're going to continue going, and so that first scenario is we're going to be going 14.14 meters per second. And I just assume that's going to be the fastest, you know what I mean? Have force first and then turn it off. Okay, so let's this is wigging with me. No, it actually would be better to have the opposite way. If this graph was the opposite, if you could have all your force at the end, that is going to generate the highest velocity. That's fascinating. Does that make sense? It still doesn't make sense to me. But let's go with it. So we're going to turn gravity off. So the thing's just going to sit there until, you know, it turns on. And oh, so that's why this on-off is nonsensical, because it should be really low. You know what I mean? It's got to be like hella low. So we can't start there. We actually have to start here. Like somehow it got to here, but just has no velocity. That's the representation. You know, you should have a little bit here. So this thing will actually get to here, but it'll just have a very low amount of velocity. And so, yeah, so we could repeat this scenario. I don't think we have to. I think this is representative. Just put this second scenario here, and then you're going to turn gravity on. Cool. And, man, the speed is going to be the same. Oh, this is wigging me out. And maybe this is kind of a fundamental property of the work energy, is that if you have a force over a distance, this is like, yeah, because work, this is energy, and that's going to be your kinetic energy, and that's going to equal 1/2 mv squared. And it doesn't matter how you do the work. If you do all the work over here or over here, it doesn't matter. The amount of work that you put in. So yeah, this is fascinating to me. So if I have a mass and I put work on it, if I put a force on it over a distance x, you know, just a 10 Newton force over 10 meters, that is going to generate a velocity. Now if I put a 20 Newton force over 5 meters for the first half, but not over the second half. And in this scenario that we're doing, we're going to get the same velocities. Man, that's kind of fascinating. Alright, so yeah, I think so weird, because I thought I was going to run into an issue just taking the average force. Alright, hell yeah. So I think we have, I have fully proved to myself that any force times distance, no matter where it occurs, is going to generate, so this is the chapter on energy. So a force times a distance, an average force over a certain distance, no matter where that's going to be, is always going to input the same amount of energy into that mass. So if you have an arrow or a mass and you're trying to put a force over a distance, it's going to, because it's a mass and you're applying a force, you're going to have a F equals ma. You're going to have that acceleration. From the energy perspective, the work energy is that if you do that, if you put a force over a distance, what we call that is work, because that's newtons times meters. Newton times meters is the definition of a joule. So you have newtons times meter, and that is a joule. So those are the units. And cool. And so that work that you put in, the output is kinetic energy. So so if you have a particle of mass and you put work on it, a force over a certain distance, guess what? This particle is going to increase in kinetic energy, and it basically just spells it out. Somebody made the equation 1/2 mv squared, or you know what I mean. Man, this is the hardest one for me to derive. I just don't have a mental. Well, I could probably get there, but anyway. So yeah, that force times distance is going to whatever that number is in joules is going to be the increase in kinetic energy. Now, if you have something that has zero velocity, hell yeah, whatever this kinetic energy is, these two numbers are going to be the same. But you got to be careful, because if we put this force times distance and we get this number in joules, this is just the increase in, this is just the energy input. So if this mass is already moving, it's only going to be the change in kinetic energy. So you would have, yeah, and so yeah, that is going to be different. I don't even know how to write that. Alright, we'll see if we can write that, because if we have an initial kinetic energy, we're going to have 1/2 mv, v naught squared, and then we're going to add this number in joules, this force times distance, and this gives us a number in joules, and that has to equal 1/2 m velocity final squared. So yeah. Alright, now I need to prove something to myself, that yeah, this number isn't just you can't just take this number and set it equal to 1/2 mv squared, and that v is not going to be your change in velocity. And only if your initial velocity is 0. So let's do an example that I can point out. So we're going to have this number be, so if this velocity was 10 meters per second, we're going to square it, that's going to be 100. Our mass is going to be 1, and then divide by 2. So this number is going to be 50, so for that energy. And then we're going to say we're going to say this number is also 50. So if we disregard the initial velocity and say that we have an energy of 50 joules, and then just equate it to this velocity, well, we were going to get that velocity of 10 meters per second. But that's not the case if we have an initial speed of 10 meters per second, giving this 50 and then this 50. This is going to be 100. We're going to take this 2 over here. It's going to be 200. And then mass is 1, and we're going to take the square root of 200 to get that final velocity. So square root of 200 is going to be 14.14. So we're not going to have a change in velocity of 10. We're going to have a change in velocity of 14. So 14.4 is our new velocity. Our initial velocity was 10, so in this case our change is only 4.14. So we're going to have a change in velocity of 4.14 in that scenario. Not just finding the energy and then setting it equal to 1/2 mv squared and solving for this. This would only solve for the final velocity or the change in velocity if the initial velocity is 0. So so sweet. So that was a decent way to look at that. Alright, hell yeah. So now, since we proved that we have this force times distance, and that's going to give us this number for energy, and energy is this kind of capital U. It's going to have units of joules, so capital U, units of joules. Now we can approximate this. So let's grab a new sheet of paper, and what we're going to do is we're going to say that, hey, in between 0.5 and 0.4, that distance, so we have a distance of 0.1 meters, we're going to have an average force, and that average force is going to be the difference between these two numbers. And so this is really cool, because after doing all that preliminary stuff, we can just get to it. We can say that 312 newtons plus 285 newtons divided by 2, that's going to be the average between those. And so we have an average of 298.5 newtons. And then we multiply by the distance it's traveled. Well, sweet. So this gives us the energy. And so sometimes, a lot of times, you'll do like U. So this is going to be U 0.5 to 0.4. You can do whatever subscripts you want. You could just say, hey, this is U1, U2, U3, U4, U5. But see how, like, this U means nothing if you just started with it. You know what I mean? That's why I start with the F equals ma, and we do this whole video up to this point. And then we're just like, okay, now I'm more comfortable with understanding that, yes, if I have a net increase in energy, the only way that energy is going to be used in this case is to take this arrow and move it with kinetic energy. Now that's not the case if you shoot the arrow straight up. Because if you shoot the arrow straight up, sure, you're going to increase the kinetic energy, but you're also increasing the potential energy. And both those have to equal that change in energy. You know what I mean? So this is going to be U1 plus, all the way through U5. That's going to increase the change in kinetic energy. So whatever the velocity... Whoa. If you shot the arrow straight up, this potential energy is really going to be negligible. Because if you're shooting this arrow straight up, the center of mass of this arrow, yes, travels this distance. And so, the force of gravity is acting down on it, applying a force in this direction. Oh man, that's tripping me out. Nah, I think it would be pretty easy. So, and that's where, the energy for the potential energy direction is just mgh. It's force times distance, which is the force of gravity, times the height, so you have just mg is the force of gravity h. So that's the simplest one to derive. And when we add up all these u's, u1 plus all the way through u5, that has to equal the potential energy, which is just mgh, plus, I guess it's the change in potential energy. So we have the change in potential energy plus the change in kinetic energy. Same thing. The only way the change in potential energy is just mgh is if we set the datum here to be 0. You know what I mean? So that's the same thing as kinetic energy. We're setting, if it has 0 velocity, we're in check. Potential energy is cool because you can always set the datum wherever you want it to be. That's useful. Okay, hell yeah. So what are we doing? So we're just going to find, so force times distance is energy. And so we're taking the average, and the average force times the distance in the direction of the force. That's the other thing. It has to be in the direction of the force, because this is an integral. It's the vector f dotted with d times r. I should look that up. Alright, so I looked it up, and it's, the small change in energy is equal to the force dotted with dr. And r is a position vector, and the force, the dot product means that the force has to be in the direction. If the force is this way and the direction is this way, well, you're doing no work in that direction. So it's only, and if you're pushing a grocery cart like down like this, and then here's the cart, and you're traveling this distance, x, it's only this component of the force that's doing work, that's actually helping. You can push all you want, you can have a shopping cart and then just push straight up and down, and just kind of like treat it like the Olympics, and you're doing like the uneven bar, or whatever that pommel horse is. We all do that. Shopping cart madness. But anyway, that's going to be a force. It's going to go straight down. It's not going to apply any work in the direction of this way. And it's actually not even going to apply any work against the Earth, because you're not sinking into the ground at all either. So no work is done in both cases. One, you're doing no work this way because the dot product says, hey, it's only the component in the direction of the distance, and you're doing no work in the y direction because the distance that you're traveling, that's zero distance. Okay, sweet. So we have that. I think I just need to just crank out a number. So let's do it. So the average between these two is going to be 240 plus 285 divided by 2. Alright, oh, this is getting... Oh, lost a rubber piece. Oh, that's a bummer. Need to fix that ASAP. Okay, so that's going to be 262.5. I'm just going to do that. We have 187 plus 240 divided by 2. This is going to be 213.5. Alright, I'm going to store these. So we're going to store them as A, B, C, D, E. Cool. Alright, so this one's going to be stored as alpha C. 265 or 262.5, we're going to store that as alpha D. 298.5, we're going to store that as alpha E. Alright, let's do this one. So the average between here is 107 to 187 plus 107 divided by 2. We're going to store that as alpha B. And then this is 0 between 0 and 107. So 107 divided by 2, we're going to store that as alpha and, alpha A. Okay, hell yeah. So we have alpha A, alpha B, alpha C, alpha D, alpha E. Okay, we're looking pretty good. And we want the total energy. So, I mean, essentially it's just going to be all those forces, all those average forces, but we're traveling the same distance. But we could do alpha A times we could do 0.1 alpha A plus 0.1 alpha B plus 0.1 alpha C plus 0.1 alpha D plus 0.1 alpha E. And I hope you can see you could have just done 0.1 times alpha A plus alpha B plus alpha C, alpha C plus alpha D plus alpha E. Same thing, and we get an energy 1 through 5 of 97.5 Newton meters. And so that was the force times the distance. That's 97.5 joules. And this is going to be the increase in energy that we're imparting on the arrow. All that force and distance is being put into that arrow. The arrow has an initial velocity of 0. And so we can say that the change in energy is equal to this U1 through 5, and that's going to be the change in kinetic energy. And I guess you could say, hey, that's going to be the kinetic energy final minus the kinetic energy initial. Initial is 0 because 1/2 mv naught squared is, you have an initial velocity of 0. So sweet. So this number of 97.5 joules is going to equal 1/2 the mass, well, I guess I'll write it out, mv squared, velocity final squared. And, we're trying to find velocity final. Sweet. So we're going to just take this 97.5, multiply it by 2, divided by the mass of 0.085. I guess we can do this in kilograms. This is Newton meters. This 2 is dimensionless. And then we have, we need to take the square root of that. And now you might be like, well, how do these units, let's slow down here. How do these units cancel? Well, if you go back to F equals MA, write the units on this. Newtons, kilograms, and then meters per second. I guess you could just do squared for now. And let's solve for kilograms. So you're just going to say, hey, kilograms is equal to Newton times second squared divided by meters. See how meters comes downstairs, but then the second squared pops upstairs. Sweet. And then so if we put that in here, we're going to have a Newton, we're going to have a meter, we're going to divide it by a Newton second squared, and then the meters goes upstairs. And look at this. You're going to have, we messed up a little bit. This is Newton meters. Kilograms. Oh, yeah, kilograms is going to be newtons. Ah, bummer. Newton meters, and then kilograms downstairs, and then we're square rooting it. That's what we should have, right? And yeah, energy. Yeah, let's slow down. Holy Toledo. So we have Newton meters. This is going to be our energy. It has to equal this energy, which is 1/2 m. So that's kilograms. And then, yeah, and we're trying to get this m downstairs, kilograms downstairs, and then we're taking the square root of it. Oh, and then we should end up with velocity after we do that. I forgot what we were solving for. We were trying to solve for this velocity final. So this is velocity final. Got a little bit scratchy on that. But yeah, for sure, newtons cancel. Then we have meters. So this is the square root of meters squared second squared. Cool. And, obviously that's going to be or you can do, not obviously, but the square root of meter squared second squared is the same thing as the square root of meter squared divided by the square root of second squared. And now you can kind of see that the square root of something squared is just itself. And so that's going to be our units. And so we're checked on units. So let's just make sure we don't mess this up. We got 97.5 times 2 divided by 0.085. And hell yeah, so we get a velocity final of 47 I'm just going to say 47.9 meters per second. And that's pretty sweet because let's compare it to our initial guess. It was just so important to do those initial guesses, even though we got, what was our initial guess with this time of 0.0233? We were going to get a 42.84, but we said it's going to be a little bit higher. So yes, so our velocity here is 47.9. And let's go back to here and see if we could actually do this one again. So we're going to have F equals ma. A is F divided by mass. So we have that 156 divided by 0.085. Store that as our acceleration. We're going to have 0.5 alpha a. We need to get our time frame. Our time frame was 0.0233 stored as alpha t. So we're going to have 0.5 alpha a alpha t squared. So hell yeah. And what does that give us? That gives us the position. Oh yeah, we were just double checking that. Wait, so how did we find the velocity? So if we have an acceleration is just a number, our velocity is just that number times t. So we have alpha a times t. That's not true though. No, that is true. Yeah, 42.7. Sweet. So 42.84. So that answer checks out. Hell yeah. And then this is the actual answer because it's not the actual answer. It's still an approximation because we're basically saying that, hey, these are linear lines between these. And so you can say that the velocity is just a little bit higher. Velocity is greater than or equal to 47.9, or just greater than, but close. And so sweet. So and I think I learned more about energy. I swear this letter U just confuses. I don't think it's useful. I don't know. I guess you got to label it something. I mean that's why that's why no one knows quantum physics, because of that letter. You're just like, oh, I'm screwed. Same thing with energy. You're just like, I'm done for. I give up. I don't think I can do anything more. I've reached my limit in physics. And so that's why we took this back to some basics. Now we're going to do one more thing. And I think I'm going to make a separate video. So this video I think is going to be done. I think separate video, I'm going to plot this in Excel and get these points. And what I really want to do is actually find the average velocity, because the center of mass in this direction should be balanced, where that whatever that line is, so in this direction you're going to have, is that true at all? I feel like that's not true. So I get that this direction, more of the mass is over here, so it's going to be somewhere in here. But why would... No, that's not helpful at all. I don't think so. Well, the fact that more of the center of mass is down here, does this mean that the... Oh, no, I'm confusing things. Oh, I'm totally confusing things. Because I'm assuming that this is a triangle. Oh, I can't do that anyway. Oh, I'm so glad I didn't waste my time. Because we did a linear approximation. We tried to find the average velocity, which is right in here. Oh, so I asked the wrong question. I thought I was trying to find the centroid in this direction. No, the centroid of a triangle is 1/3. I would have got, at the end of the day, I would have got a value that was down here, and I would have wasted an hour. So this is pretty sweet. So actually, I think I need to figure out, I think there's an equation where it's just like, hey, if this is all these points, and you know, like most of the points, like this, let's say you had something like this, you know, and this was 0 and this was 100. Well, what's the average? You know, and let's say you just have a small little change here. Well, it looks like you're going to be pretty close to 100, but, you know, maybe a little bit less. And so, you know, so I think there is a way to take an equation and be like, where are all the numbers? I mean, if this is 0 through, yeah, I think you get what I'm getting at. But like, what's the average? The average... Alright, sorry about that. Camera cut out. But yeah, we kind of figured it out. I did a simpler one where we have a square of 100 and 100, and we're going to go ramp it up from 98 to 100. Obviously, the average force would be 99. So if we sliced all this up, you know, we would have 98, 98.1, 98.2, and we would just add up all those values. Once we add them up, we would divide by the number of slices that we took. And so that's very representative of, yeah, so we would do the same thing here. I just don't know how to actually do that mathematically. I'm gonna look that one up because that would be a good skill for me to have. I don't know how complex that would be. Like, what's the average? Does that make sense? Like, what's the average value of, because even if I have, like, x squared, like 1, 2, 1, 2, 3, 4, and I go up to here, look at this. The average value, you know, even though this is 4, and this is 0, and this is 1, but look at this. Your average value is, I would say, I mean, yeah, we could figure that out. You could slice it 0, 1. Oh, this is interesting because this goes back to, like, how do you slice things? Do you slice it like this? Do you go 0 and then this is 0 and then 1? And then your average value is 0 plus 1 divided by 2, and that's going to be 0.5. So 0.5 is your average value. Or do you say your average value is 1 and 4? That's going to be 5 divided by 2. That's going to be 2.5. Or maybe it's halfway in between 2.5. Alright, hell yeah. Or maybe it's kind of just halfway in between 2.5 and 5, which would be 2.5 plus 0.5. That's going to be 1.5. So maybe the average value of this is 1.5. And, yeah, and I still don't... I'm not quite sure... yeah, it's kind of interesting. And it's tripping me out because it's not the centroid. It has nothing to do with the centroid. You know, because if I had this same shape and this was the force, 0 to some number, the average force is right in between. If it's just a little bit less, hey, it's going to go down. If it's a little bit more, it's going to go up. And it has nothing to do with the centroid. So yeah, that's going to be for another video. So thanks for joining me on this one. And hell yeah.